Hello friends, this is Mowgli. I will be talking about ARM-based development. This session is the first session of the course, and welcome you all to this course. The outline of this course is given here. I will not go into the details of each of them. Basically, this course intends to cover architecture of ARM and then assembly language programming, how to use ARM assembly language to program various applications, and then it will also talk about other modules like memory management, cache, and peripheral devices, and including some support which will also be covered here. And the course intent is to give you a good overview of processor architecture by taking ARM as an example and then running you through various features of ARM and then explaining the assembly language programming part of it so that you understand the concepts behind the ARM architecture and how it has been evolved, and give you a good overview of embedded systems as well, and tell you how to use various modules and peripherals and to implement an embedded system which would be ARM based. But this knowledge what you gain by going through this course, you will be in a position to understand any processor architecture as well to design any system based on any processor. Welcome you all, and I hope this will be very useful to you, and I will enjoy this course. Let me go through the introduction. It imparts knowledge on processor architectural concepts, provides detailed study of ARM architecture as an example, and gives you how to write assembly language programming, how to use the support provided by assembly language of ARM, and it talks about bus architecture developed by ARM, and memory hierarchy and cache systems will also be covered here, and peripherals which I mentioned earlier. This basically has around 40 hours of lectures along with lab sessions using an ARM simulator, which will give you a good hands-on experience of using the assembly language of ARM, and it helps taking up any ARM-based design or any other embedded processor with embedded systems going further. The focus of this first session is to give you a top-level view of what is a digital computer architecture and what are the different types, and then we'll talk about some instruction set architecture and two types of them which you might have heard about already with concept, and then it will give you a brief overview of ARM and then where this ARM core IPs could be used and how the whole ARM ecosystem has developed over the last 30 years, and which has in fact overwhelmed the embedded market, and it has reached a stage where whatever embedded products you have, in fact if you are holding any mobile or laptop or iPad in your hands now, most probably that it is built based on ARM based ICs. Let us talk about computer architecture. All of you are aware that a computer has some CPU, that is central processing unit, and a memory associated with that. And the CPU and memory are connected to two buses: instruction bus, data bus, and address bus. Now the CPU uses the address bus to access the instructions stored in the memory, and these instructions are understood by the CPU. When it comes into the CPU, then it interprets and decodes the instruction and executes the instructions which will perform a useful function. Now for an example here, a program counter is a pointer which points at address of a instruction, and it fetches that instruction and executes it, and according to the instruction it throws some result back into the memory. So here I have not shown the instruction and data memory separately, which we will talk about it as we go forward. Basically the computer architecture has evolved with two basic differences. One is 191 model, who is the person behind this invention, he has designed a system with memory and CPU attached with a single bus. This is the data bus and this is the address bus. Now the memory is holding both instruction and memory and data together in a single memory system. And whenever the CPU is sending out the address for the instruction, that is specifically the same memory, and based on the instruction, if any data needs to be saved into the memory, that same data is also using the same address and data buses to access the memory to put back the result or read any status or any information that the CPU is processing is also read from the memory. As you see in this system, the limitation is that the same bus carries both data what is needed for the software as well as the instructions to the CPU. Because of this, at a single memory cycle, both cannot be happening simultaneously. As you understand, the instruction fetch and the data fetch need to happen together. And in this case, because of the limitation of the physical bus connecting the memory and CPU, they cannot go in parallel. Let us see. The same memory holds both data and instructions. The CPU fetches the instructions and data from the same memory using a common bus. Code and data accesses cannot happen in parallel, which reduces the speed due to this limitation. The PC, which is a program counter pointing to the instruction which is being accessed by the CPU, gives out the instructions, gives us the addresses one from the other, and the instructions are read and decoded by the CPU. Now, as I mentioned, because of the common memory, there are some limitations. The Harvard Mark I is another processor architecture design which evolved from the one-line architecture by splitting the data bus and the instruction bus and data bus into two different locations, two different buses, and then the data and program are kept in two different memories. Because of this, the access to the program as well as access to the data can happen in parallel. As you can see, this improves the parallelism, and this computer, which is based on Harvard architecture, can perform more operations and it can do better than compared to one-on-one architecture, which we mentioned earlier. Now, just to give you a brief overview of Harvard architecture, their memory and signal pathways are different for both instruction and data. The CPU can read both an instruction as well as perform a data memory access at the same time. A Harvard architecture computer can thus be possible for a given circuit computer because it can do both simultaneously. In a Harvard architecture, we don't need to keep the same memory configuration for both data and memory. For an example, instructions need not be changing, so that can be saved in ROM memory, which is a read-only memory, and data can be kept in a random access memory, which is supposed to be modified by the program. So we don't need to keep the characteristics of the memory same for both instruction and data. So that gives a freedom for the system designer to choose the memory which is required from the instruction point of view or from the data point of view in terms of access time or in terms of the bit. We can decide which memory to use for instruction and data, and that can be used in the embedded system that we designed using the Harvard architecture based chip CPU. So because of this flexibility, most of the modern computers and architecture are Harvard architecture based. Now we'll talk about instruction set architecture. You might have heard about ISA in your earlier courses on computer organization. This is the programmer's view of a machine, and which depends on answering the following 5 questions. How are instructions encoded? Now I spoke about instructions and data. Now we are going into the detail of how are we going to encode the instruction. What operation the CPU needs to perform? Is it an add operation or a move operation, or is it supposed to do any multiplication, or it is supposed to perform a load or store of the data is the data memory. So how do we encode this information in the instruction format? So that is a part of defining a structure for this is part of the ISA, that is instruction set architecture. Now, how is data represented? As we know, in a computer world, we use both integer data as well as real data. Wherever scientific applications and graphics and other gaming related data needs to be processed, they happen to be in floating point, and we need more precise and high precision data to be handled by the CPU. So there is a representation for integer and there is a representation for floating point as well. So how this data is represented in the system, how they are used, is also decided by the ISA. And when I say data is stored in the memory, there are so many ways that could be stored, and we will be talking about that in the coming section. So this also is designed based on the it's defined in the ISA, and if we say that a processor follows a particular instruction set architecture, they all do the same thing simultaneously the same way. Only thing is these different architectures may have different modules attached to that, and how data can be accessed, which is stored in the memory, and what operations can be done on this data. Let us see one by one what they mean. Now, ISA refers to the programmer's visible instruction set. It defines the boundary between hardware and software. And we say that ISA is identified by the processor architecture. And when we go into details of the microarchitecture, it talks about how a separate internal organizational processor is designed. So ISA doesn't talk about the internal organization. The processor microarchitecture talks about it, whereas ISA only talks about the behavior and how data needs to be represented, and how it has to be accessed, and how the coding of the instruction needs to be done. Now, for an example, take data needs to be can be of any type, as I mentioned, integer or floating point or multimedia data. Then there are different integer data formats, both signed and unsigned. We will talk about this. You might have heard about about ones complement, two's complement, and time magnitude format. These are all the different ways an integer can be stored. Now, which of this format is being used by the processor is designed by the instruction set architecture. And you have heard about BCD numbers, which is binary coded decimal. If you have seen LED displays, where the numbers are displayed on the digital clocks or any of the digital systems, they represent numbers from 0 to 9. So how these numbers are coded so that you will be able to access the binary coded decimal in the architecture is also defined in ISA. Now, floating point, which I mentioned, this is the IEEE standard. We will be touching upon this format also in the coming lecture. And multimedia data, there are so many ways that every pixel in a graphical representation, a graphics processor will be defined here, and it could be a category floating point number used for 3D graphics, or it could be a high precision numbers of 64-bit or 80-bit. Now, we talk about representation of data. Now, we need to store it in the memory. That there are two ways of storing it, which are called big endian and little endian. Let us not go into detail. We will talk about it in the subsequent lecture about these two representations. And then, in any typical program, there are different address spaces used. You know that there are spaces required for a program, that is called store space and a data space. Apart from that, there is a stack requirement and heap requirement. If you have done any programming, you would have heard about all these things. Anyway, even if you are not aware of these specifically why they are used and what they are used for, the next lecture I will be talking about how to use these spaces in a program and how they all tie together in building a complete software program. I will be talking about in the next lecture. And then the ISA also defines the register file. This is the placeholder for storing all the data which is accessed in the memory while the CPU is processing them. So this is the registers which are inside the CPU, and we talk about that subset part of it. And apart from this, the floating point numbers, there are different bit 32 or 64-bit or 80-bit floating point registers are there based on the requirement on the position. except for the registers, all our address spaces are individually mapped onto contiguous memory address spaces in the memory. Let us go to the next slide. Now, having discussed about flowing of data, let us discuss on this how the data can be accessed from the memory. As you know, when an instruction is getting executed, there are different modes in which the data could be accessed. And for a typical processor architecture, there are so many ways these addresses could be accessed from the processor. And these are all some of the addressing modes. We will not go into the details of them. And when we talk about ARM architecture and when we talk about the data processing instructions, we will go into the details of each one of them. Now, all the addressing modes which are supported here are also there in ARM processor, and we will be touching those in the subsequent lecture. Now, having talked about ISA, there are two types. Basically, the major differences are there. The way the instructions that architectures are defined. There are two school of thoughts. And earlier in 1980s, the CISC type of instruction ISA was evolved, and from CISC, the processor architecture moved into RISC processors. Let me explain what is CISC. It is a complex instruction set computer. As the name implies, the instructions are much more complex. What I mean by complex means there is a one single instruction defined which will perform multiple operations together. Now, there are many addressing modes supported, both involving registers and memory, and support for many complex operations, both on integer and Boolean data types as well as strings. If you have heard about 8086 processor, you might have come across string operation which perform comparison of strings, and then when you give two pointers and they do the comparison, one instruction is there which will compare to strings. So the time taken for executing that instruction varies based on the number of characters in the string. So the complex instruction set architecture tries to keep so much of operations in a single instruction, and because of which every instruction might take various number of cycles to be for completing that instruction. Because of that, they are data dependent as well as particular operation which is being performed. So that's the reason why it's called complex instruction set. Now, the data processing instructions with operand either from registers or memory. So there is a common instruction, and there are given where the operands could come from a memory or a register. When you say operands, just for an example, if you are adding two numbers and then writing the result into another register, those two numbers are called operands, and we could read it from either a register within the CPU or other operand could come from the memory. Now, what do you mean by variable length instruction? That is, as I mentioned, because of the complexity of every instruction, the amount of bits or bytes needed to encode what needs to be done by the instruction and what is the record data along with the instruction need to be given varies compared to what the particular instruction is designed to perform. So because of this, typically in a complex instruction set computer, you will see the instruction length, that is the binary bit held by the instruction, occupied by the instruction, varies from one instruction to the other. Because of the complexity, the execution of each instruction varies, and as you understand, because the instructions are complex, the digital logic needed to be implemented within the processor for decoding the instruction to know what it is supposed to do will also be complex. When I say a particular design is complex, that means the decoding logic for understanding the instruction is going to occupy more real estate within the chip. That means it needs more digital logic within the chip to be built to understand the instructions coming from the memory. Now, what is the advantage of the CISC operation? There are some advantages because multiple operations are encoded in a single instruction. You get a better code density when you use those instructions in the application. What I mean by code density is the amount of space occupied by the code when you compile your high level language or an assembly instruction. When you assemble it and then get a binary image, that will be much smaller because the compiler or assembler would have chosen a correct instruction for performing your job, and effectively we get a better code density because of that. Now, what do we say? Sys has less number of general purpose registers for a given technology. The reason being because we have already spent a lot of chip area in designing the decode logic as well as other required digital circuitry within the chip to perform these complex operations. The effective space required are available for keeping the general purpose registers in the CPU have come down. Because of that, normally you tend to see for a given technology, the general purpose registers which are available on a CISC processor is less compared to a RISC processor. What I mean by given technology is that you might have heard about 190 nanometer or 90 nanometer or even the 28 nanometer chips are coming out now. These are the different technologies which enable keeping a digital logic building into the chip. So as the technology improves, the complexity as well as the number of transistors that could be built into the chip is going up in millions and billions. Now, when you are comparing a CISC and a RISC processor, we need to keep the same technology in mind and then see whether the number of registers supported by these processors are the same or not. When we see that, we normally tend to see that CISC processors support less number of general purpose registers because of its space is occupied by or consumed by other complex circuitry in the system. A very important thing part of that is the decoding of instruction, the logic required for decoding the instruction. And examples are the earlier x86 family processor and Motorola 68K. Now let us talk about reduced instruction set computer. This architecture is actually the ARM is also based on this, and the data processing instructions only support the operands registers. What I mean by this is that when you have an add instruction in the RISC-based system, the two operands come for an add instruction need to come from two registers which are within the CPU. There are no add instructions or any other arithmetic instructions or boolean instruction supported in a RISC-based system where one operand could come from a register and another operand could come from a memory. You would wonder, how does it reduce the decoding logic of these instructions? If we need to encode information about the two operands in an instruction, if suppose a particular processor gives 16 CPU general purpose registers in it, we hardly need 4 bits to represent where this operand is coming from. Whereas, if the instructions need to support operands coming from memory also, then we need to say where this operand is in the memory. Suppose if memory is what the maximum physical addressing capability of the processor happens to be 32 bit, then we need to mention the 32 bit of location address needs to be mentioned in the instruction to say where the other operand is coming from the memory. So basically what I mean by that is that when you have operands coming from memory, we need more bits in the instruction to mention where this operand is coming from. And because of this, our decoding logic also increases and our instruction bit also changes based on the operand. So RISC do not have that kind of a requirement. And you may wonder, if all the operands are coming from registers for data processing, then what is the need for a memory? So then the memory is holding the operands, but prior to doing any operation on it, that need to be brought into the CPU, and then other data processing instructions need to be used to operate, to perform any operations on those data. Now it can really easily, you can see that Because of this, we are adding more instructions. Suppose if you want to add two numbers, one happens to be in the memory and another one is in the register. Using a RISC processor, we cannot perform this operation using single instruction. So we need to have one instruction to bring the data which is in the memory to a register and then perform the operation that we want to do. So RISC computer, to perform the same operation, we need more instructions. So, but the processor that needs to support the number of instructions in the encoding have come down because we are not giving too many options for operands to come from memory. Once we give multiple options to take the data from memory, we need to support all the other things more associated with that. Because of that, the number of instructions explode more when we support operand access from memory. Now, how does this manage to have fixed length of instruction? Because the operands are coming only from the registers, we know how many registers are in the CPU, then the number of bits required to configure the operand's source location or the destination location is fixed. So the RISC computer can afford to have fixed length of instructions. When we have fixed length of instruction, the decoding logic becomes simpler. So the amount of space or the logic spent in decoding the instructions have come down drastically compared to this processor. Now, as we simplify the decoding logic, it also increases the speed with which that instructions could be decoded, and because of which any instruction, most of the instruction I would say, can be completed in a single cycle of execution. Now, as I mentioned, to perform the same operation, we need multiple instructions. Naturally, for a given functionality, the code size increases in the RISC processor. Now, you may wonder if the code size is increasing, how is it better than RISC? But the reason being, we have simplified the logic inside the CPU. We are able to run it faster, and we are able to complete the instructions in a single cycle. Most of the instructions in the single cycle, even if number of instructions are more in a RISC processor, the effective performance throughput that we get from the RISC is always better comparatively to other complex instruction set computers. And one more advantage of a RISC processor is that we have simplified the complexity in the coding logic and decoding logic. So because of that, we have more chip area to be used for keeping lots of general purpose registers in the processor. And what is the advantage of having more processors in the chip? We can afford to keep the operands that are coming from the memory for longer duration in the CPU register while the program is operating on them. Because of that, the need for the program to go back to the memory is coming down because we have enough number of registers to operate. So effectively, this reduces the memory accesses and increases the performance of the system. And some of the examples of RISC are made this architecture, but I am just touching the ARM on it here. So let us now touch upon ARM. As I mentioned, ARM supports RISC. I'll give you a brief overview of ARM and where ARM processor is in terms of the embedded system is, and then we will go into the details of the architecture later and the subsequent sessions. So ARM Computers is a first company which has been established in Cambridge, working on processor architecture, and they came up with the first CPU, which is named as CPU 6502A, and these were the characteristics of that processor which came out of ARM Computers in England. As you see, it is came in 82, and during that time the processor architecture was evolving from the 8086 to other higher line processors in the Intel family, and subsequently other Motorola and PPG and other processors were also evolving during that time. So the speed as well as the size of RAM and ROM what you see in this for a general home computer is much lower than what was needed or required because of the requirement of the processor performance. So Acorn Computer decided to set up an advanced research and development session specifically to work on risk-based system, because during that time the risk was in the research institutes. They were debating that why not go deviate from the risk way of implementing processes to a risk where you simplify the processor architecture and increase the performance. It was a revolutionary idea at that time, and exactly took on that, and it was successful in coming up with the first telephone in 1985, and it was built with just 25,000 transistors in it, and that was the first commercial risk implementation, which really revolutionized the architecture, computer architecture arena of that. And I thought I will share the core, ARM core, that was designed by Acorn here. And let us see. From there, it went on to start a new company, which is called Advanced Risk Machines in 1990. And the goal of that company was to build a low cost, low power, high performance specific risk. Why do we need low cost and low power? Because we wanted to build chips which consume less power so that it can run on batteries, and the mobile phone or a laptop that you are holding, and you like to have them running for longer duration without going for charging them more often, and this 32-bit risk processor help you in making that dream come true. Now, ARM decided to build processor cores, but they were not making the chips based on their own code. They do not have a path. What ARM does is they concentrate all their energy in coming up with new architecture, innovative architecture in a low power, low cost for a low power, low cost market, and give that processor design as an IP core to other chip companies who integrate that ARM core along with their other peripherals and application specific co-processors and build a chip. So ARM is not making ICs, but their presence is there in every chip that is coming out in the Indian market. Now, what is IP? All of us know that it's intellectual property, but how is it used by ARM? So IP means that it is owned by the company which designed the chip. So ARM, which is coming up with such a design for a processor, it owns the IP with it, and what it does is it makes those designs and gives to the IC design engineers in other companies who build the chip based on ARM, and the ARM core IPs are integrated with their some other suitable glue logic. Either it could be provided by ARM or it could be developed by the individual companies who buy the ARM core IP, and the complete chip is built using that. The core IPs could be a microprocessor like ARM, or it could be other special function co-processors like DSP or Ethernet, peripherals or ARM, other processors cores. Now there are two types of IP cores. One is a hard IP core. What I mean by that is that a chip is completely built, even excluding the plastic package around it. So this can be used as a single entity into any other design. So because of this, the electrical characteristics are fixed when this IP core coming out of the ARM, or it could be any company who is doing a business in a hard IP, and their size and functions are fixed because the technology that they have used for building this chip is already done and the chip is ready now. So the shape means the size, you know how many millimeters or square millimeters of size, that is also fixed, and the process, silicon process, I mentioned about 90 nanometer or 48 nanometer. So that technology they are used for building the chip is also fixed. So the company which buys the hard IP core need to follow a similar technology to build a chip around it. Now we want the customers to have much more flexibility when we give any product out. So I'm also thought of giving a soft IP core so that the customers who buy this IP core can do some changes to that, but they can change only the size and shape of it, but not the other design characteristics of the design. That means this soft code, though it is given in a source code format, they are not supposed to be modified by the end customer who is taking the software IP from the company which is providing it. So there are no legal rights to alter the hardware, the source code of it, and often the source code is encrypted to protect the IP. So you may wonder what is the flexibility that we get from soft IP code. When we are integrating any third-party IP into a chip, the flexibility that is required not to change the internal design, because if we are going to make any changes to the internals of IP from other third-party companies, then that could have been done in the company itself. So when we buy this, any company doesn't want to change anything, and even the company which is providing the IP doesn't want the company to modify anything. But the flexibility here is that we could place those IP based on other peripherals or other process application specific circuitry in the chip, and we see if the customer is able to make any changes to the size or the shape of the IP, it could be fit well into the chip, so that the final design is coming out performing well in terms of speed and power dissipation. So this advantage is got by providing a soft IP core. Now there are some reference methodologies which ARM is providing by working with the tools company, EDA companies, which you might have heard about the electronic design automation companies. So it is not that we can just buy IP and build into a chip. So we need to make sure that there are tools supported for that. So ARM already has a tie-up with all the well-known EDA companies, and they already make those tools available and libraries available so that the end customer could buy the soft IP from ARM and they could integrate with their chip. Now let us just touch upon ARM design philosophy, how they have differed from the rest of the processor companies. The philosophy is that it is very simple and powerful, and the whole family of processors sharing similar design principles. That is, the ISA is mostly common across different families of processors coming out of the ARM, and there are so many design chip architecture IPs which were bought by well-known names in the market, and IPs are integrated by other chip vendors in their designs to build a SoC along with their peripherals. Now this is to just give you a naming convention that ARM follows. Maybe when we talk about individual ARM ICs, we go into the details, but this gives you an overview of how to realize what are the features are supported by a particular chip when they say that these are the name of the chip that is IP converted. Now, as I mentioned, ARM is a service-based system. It is having powerful instructions, but most of them, I say most because some of the instructions in ARM do not execute in one cycle. I will talk about that why they have deviated from the risk to get a better performance and the requirement of application developers. Now there are basically some high-level design guidelines, instructions. It's a reduced set, as I mentioned about the risk, and most of the instructions for complete in single cycles, and they're all fixed length. And the pipeline, the decoding is done in one stage. As I said, the risk decoding is simpler, so it could be done in single cycle. So microcode is another which takes more cycles to understand the complex instructions, but because this is a risk-based system, there is no need for a microcode, which is again a smaller set of program written to understand a particular instruction to execute them inside the processor. And as I mentioned, it has got large set of registers, and this is very important thing to remember, that all the memory accesses are done using only two classes of instructions which are called load and store. That is the typical of any RISC-based systems. And because of simple design, it can run faster. And as I mentioned, there are some deviations which I will talk in the later session. Now, it's a smaller processor for low power consumption to be used in embedded systems. The target market is for embedded systems, and it can also ARM also has a separate mode called thumb mode, which is a 16-bit instruction, whereas the typical ARM or 32-bit instructions. So this high code density design is for thumb mode, where the instruction bit is reduced and the features which are supported also reduced there. So which are suitable for a very low power requirement, embedded system requirement. And this also provides different kinds of memory can be interfaced, because the way the memories are interfaced with the ARM code, there is a lot of flexibility and programmability supported in the ARM, which helps in configuring or building a system using any low cost slow memories as well. And it's having a reduced die size for a particular manufacturing, and the cost of the manufacturing is also less because of that. And there is a whole lot of support given by ARM for developing real-time applications. What I mean by that is that when we need to develop real-time applications, we need a lot of support in debugging them and trying to make sure that the application that we develop sticks to the real-time requirements, and the tools supported by ARM gives you all the flexibility, as well as the architectural supports are also given to take care of the RTOS real-time OS requirements as well. Of course, no processor can be successful in the market without a proper support, and ARM has a worldwide support network as well as a whole lot of ARM ecosystem built, which helps in coming up with ARM-based systems in a much easier way. Before we end this session, I just want to show you the ARM ecosystem which is there in the market now. There is an ARM Technology Access Program. Basically, this is a framework for selecting and enabling competent design centers which are capable of buying the SoC from ARM and building a system on their own. So ARM has a fixed method of doing it, and there is a whole lot of companies who are part of this program. This is one of the strongest support networks in the design industry, and we have ARM community which with lots of partners, and the support is also coming from ARM as well as third-party partners doing a design services support. So if you spend some time on identifying each of those company logos, you might see every company in the embedded domain, either from OS or from the chip companies. You could see them here. Maybe I can point out to some of the companies which are well known, Motorola, Sony, Sharp, and VLSI. There are plenty of semiconductor companies as well as RTOS vendors like UNS and Wind River, and you name anybody. These companies are there who are part of ARM and who are using the ARM-based systems in their products. So, what are the market landscape? This is the latest news in 2004, early 2004, that over 50 billion ARM powered chips have already been shipped so far. This is one of the key achievements, I would say, that in the ARM based system. Now you understand, knowing ARM is how important, because it is all over the world, and knowing ARM processor architecture and understanding their features and knowing how to program using ARM will certainly help anybody in this embedded area to be successful in the market. And this is one of the most licensed processor cores in the world, and it is used in any embedded products that you come across. GBA, as all of you may be interested in gaming, and you would be surprised that these are also built based on ARM based system. So we are going to learn more about ARM7, which is the 32-bit RISC architecture, and there are subsequent family ARM family processors. Once you know internals of ARM7, knowing them other processors would be easier, and it will be helpful for you to know this, so that you understand the later future processors also. So in this lecture we will concentrate more on the internal of ARM7 as well as some of the specific features supported by ARM9. Then there may be one or two sessions maybe to talk about the future ARM processors and how they are evolving into the support required for 64-bit processing and other GPU and graphical processors. Those things will be covered in the last session. And more than 75% of the 32-bit embedded processors are ARM based. Maybe it could be more at this moment, and it is especially in portable devices because of its key design criteria that ARM wanted to build a low power. So which has helped in terms of achieving 50 billion, because that number of mobile phones in the world is increasing, the mobile connection and the mobile equipment. So the company which has designed a processor specifically targeting the low power market is able to do well in terms of the market position. And these are the latest products which have come out, which are all ARM based. This is taken from ARM source. And for this course, I would be referring to two books which are given here, and I will also be referring to the manuals which are available on the ARM website, and we will talk more on ARM7 assembly programming, and then we will talk about other ARM9 and memory management and cache systems in the as a part of this course. And this is just to give you a summary of what we have covered today, and looking forward to an interesting session to talk about more into details of ARM and how it has captured the market, as you have seen in the slides today. And it was fun talking to you. See you in the next lecture. Thank you very much for your time. Have a nice day. Thank you.